Hi everyone, let me welcome you to the 20th session on ECT 204 Signals and Systems. In the last video you have seen an introduction to the Fourier series and we computed the Fourier series of a square signal. And we appreciated the demo with Python and we understood the meaning of Gibbs phenomenon. Now in this video we see the Fourier series of a ramp signal. With this you can do further exercise and understand the theory of Fourier series. Today's speech is organized into your learning outcomes, computation of the Fourier series of a ramp signal and the line spectra of the ramp signal and the summary of understanding, of course with a Python demo. Your learning outcomes are you will compute the Fourier series of a ramp signal, then you will appreciate the Python program code and realize it with the first 10, 25 and 100 components, and then you will understand the Gibbs phenomenon the same way you did for the square signal. Now let us consider this ramp signal, this as a period of t, capital T, and an amplitude of v. Let us compute the Fourier series for this periodic signal. Now during this interval 0t, this function is realized as v by t into capital T minus small t, because when t equal to 0, its value is v. When t equal to 0, its value is vt by t, that is v, and at small t equal to capital T, its value is 0. So this is the definition, or this is the definition of the function in one interval. So xt during one interval, that is v by capital T into capital T minus small t. So now I can compute the Fourier coefficient ck as 1 by t, 0 to t, xt raised to minus j, 2 pi kt by t. This is omega 0 is nothing but 2 pi by capital T. So dt, so that this becomes v by t 0 to t capital T minus small t raised to minus j 2 pi kt by t dt integrated from 0 to t. Now this integral I can compute with the integration by parts, which says that this integral will be the first function into integral of the second function minus integral of derivative of the first function into integral of the second function. So here I will take the first function as capital T minus small t and e raised to minus j 2 pi kt by capital T as a second function. So this v by t is common to both terms. So I will take this v by t outside and I will take this first function here, that is capital T minus small t. Then integral e raised to minus j 2 pi kt by capital T, all from limits from 0 to t, minus integral of derivative of the first function. Derivative of this function will be minus 1 because it is a derivative of capital T minus small t with respect to t. So it is a minus 1. Then derivative of the first into integral of the second. So integral this function, integral of the second function comes here. Now if you look into this, the first time will be v by t into capital T minus small t into, if I integrate this function, I will have a t by j 2 pi k here because minus t by j 2 pi k here. Into e raised to minus j 2 pi k by t, or integration limits are from 0 to t. Then this minus v by t is here into integral from 0 to t minus 1 into this integral will be e raised to minus j 2 pi kt by t with t by multiplied by t by minus j 2 pi k. So that minus t by j 2 pi k into minus 1 will become a plus t by j 2 pi k. This is integral from 0 to t raised to minus j 2 pi kt by capital T dt. So when I apply the, let us look at the first term. When I apply the upper limit, small t equal to capital T, the old term vanishes, because when t equal to capital, small t equal to capital T, the old term becomes 0 because this t minus t becomes a 0. Now then if I apply the lower limit to 2 pi kt, If I look at the lower limit, if I put a small t equal to 0 here, this e raised to, this becomes e raised to j0, that's a 1. So here t equal to 0, so I have a t square by, then the negative sign will appear because this is a lower, will disappear because the lower limit, this is a lower limit, t equal to 0 is a lower limit. So this becomes t square by j2 pi k, okay, into v by t, minus this will be v by j2 pi k into, this integral will become e raised to minus j2 pi kt by t by, into t by j2 pi k. So this here this t is cancelled, then there's a t here, so that will be cancelled by the t upon the latest integration. So there's a minus sign here, so all these things becomes plus, then this j becomes a minus sign. So this limit, this is e raised to minus j2 pi kt by t from 0 to capital T. So it will be, when I apply the upper limit, it will be e raised to minus j2 pi k, and apply the lower limit, it's a e raised to 0, that's a 1. So both upper limit and lower limit are 1, because it is e raised to minus j2 pi k, k is an integer, so e raised to minus j2 pi k is cos 2 pi k plus j sin 2 pi k, that's 1, always 1. So upper limit is 1 and lower limit is also 1, so this second term simply vanishes. So what do we have here? It is vt by j2 pi k, vt by j2 pi k. Now I cannot get C0 by putting k equal to 0, because when I put k equal to 0, it becomes a 1 by 0 term. So what I can do is I have to do a separate integration for finding C0, that is integral from 0 is integral 0 to t xt dt, that is the area under the curve xt. So what is the area under the curve in one, because this has this triangular signal with a height v and width t, so it is half vt is the area under this curve, half of vt is the area under that curve, so it becomes half of vt, okay, and ck is vt by j2 pi k. So c1 is vt by j2 pi k, and c minus 1 is minus vt by j2 pi, and c2 is vt by j4 pi, and c minus 2 is vt by j4 pi, c3 is vt by j6 pi, that, and so on. So what will happen? If you look here, if since Cn equal to minus C minus N, An equal to 0, because it is Cn plus C minus N. If they are negative, then An equal to 0. Then Bn is equal to J times Ck minus C minus K. So Cn is Bk is J. Cn, since Cn equal to C minus C minus N, An equal to 0, and Bn is J times Cn minus C minus N. So what I can say is, since Cn and C minus N are equal, it becomes J times 2 Cn. So I will have this B1 will be twice of this C1 multiplied by J, so it becomes Vt by pi. B1 becomes Vt by pi, B2 becomes double of this multiplied by J, that is Vt by 2 pi, Vt by 6, Vt by 3 pi. So since B1 is Vt by pi and B2 is Vt by 2 pi, B3 is Vt by 6 pi, B4 is Vt by 8 pi, etc. So that I can see that since An equal to 0, there are no cosine components, there are only sine components. So this becomes this contains a DC time plus a sinusoid solely. So the DC so xt becomes a DC time, that is half of Vt, plus here I have the first harmonic, that is Vt by pi sine 2 pi t by capital T, that is A sine 2 pi t by t, plus Vt by 2 pi sine 2 pi t by capital T, plus Vt by 3 pi sine 2 pi into 3 t by capital T, plus etc. Now let us observe a demo with Python. Now here I have Here I have the Python code for this. I have imported the SciPy, numerical Python, pylab, etc. And I have a time axis, say from 0 to 50 with increment 0.01, and a time period I take as 20, and the amplitude I take as 1. So x is equal to v star mod t minus t comma t. That is my that's my ramp signal. Then let us consider that I take the first two values, first two components. So here sum is equal to v star c, because c equal to t by 2, because I initialize the sum with the DC value, that is vt by 2. I initialize a sum with the DC time, that is vt by 2. Then while a is less than n, I append this t divided by a pi sine 2 into a pi into t by t. Okay, so this is my Fourier coefficient, and this is a sine time there. Then the sum is added with this b, and every time a is incremented. Now I try to compute the error between the two signals. That is just my no, I have this d equal to c minus b. So this is added with the signal. Okay, so I plot the sum here. So I'll open a terminal here. I run this code. Here you can see that the two signals do not match well. So I can add more time, say n equal to 5 times. Now you can see that the Fourier series comes closer to my original signal. Okay, there are 5 times now, the 5 sinusoidal times now. Now it is nearing the original signal. Now let us add 10 times. Now you can see that it is becoming closer to your original RAM signal. The blue signal is your Fourier series approximation, and red is your actual signal. Now we take 100 times. You can see that it is getting very close, but here you can observe the Gibbs phenomenon here. Here you can see that at the edges you can see many oscillations occurring at the edges, at discontinuities. But during the continuous period you can see that there is a great agreement between the actual signal and the Fourier series. I will make it 1000 times. Here you can see that even with 1000 times at the discontinuities, you can see these oscillations. This is a Gibbs phenomenon. but during the continuous case you can see that there is great agreement between the actual signal and the Fourier series. So you can copy this code and you can try this at home. Now let me go back to my presentation. Now you can have a plot of ck square or mode ck square against k. You can see how the energy is distributed between different spectral components. You know that there are only sign terms, and these energy is plotted between different different spectral components. So let us see how the energy is distributed among different spectral components. I have another Python code here. Here I am trying to plot the spectral component mode ck square against k. So here I have a indices k from say minus 10 to 10 with increment 1, and here I take v equal to 1 and t equal to 1, and this spectrum value or mode ck square I write into a blank array. So for k in int is this value. These are values from minus 10 to 10. And if k equal to 0, s value is nothing but half of Vt. This is the value at 0. That is a DC value. S value, that is Vt by 2. If k not equal to 0, s value is Vt by Vt divided by j 2 pi k. I have omitted the j because this real value I am plotting. Mode ck square I am plotting. So it is Vt by 2 pi k. This is star star minus 1. This is an inverse. So this is basically Vt by 2 pi k. Now the absolute value of s value square is taken and it is appended to the blank array. So after this, after the full iterations, s val array will contain mode ck square for different value of k. Now I can plot this mode ck square in s val arr against the index, and you can give some labels. These R prime etc. are for typesetting the labels in LaTeX. Then the grid is true and show. Then I can compute the sum of this s val array. That will give the total power in the signal. Okay. So let us run this code and appreciate that. Now we can see that how the energy is distributed. You can see that 1/4 of the energy is in at k equal to 0, that is in the DC value, because you can see that there is a DC offset in the signal. And at k equal to 0, it is around k equal to 1, it's around 2.5%. Okay, this is a 25%, this is a 2.5%. This k equal to 3, it is much less. You can see that the signal tapers off, or the signal energy tapers off as we go to higher values of k. You can see that the DC component, the first and the second side lobes are very strong. Now let us compute this p value. You can see that it is some it should be around 1/3, 0.333. Now it is approximating to 0.328 because I have taken only 20 times. That is why it is coming to 0.328 something. Now let me go back to my presentation. So this is how I appreciate the line spectrum of my ramp signal. Now the summary of understanding. Here in this video you compute the Fourier series for a ramp signal. Then you realized with the first 10, 25 and 100 or even 1000 components with Python, you understood the Gibbs phenomenon. Then you understood the line spectrum of ramp signal. And that is the end of this presentation. I thank you all.